Hello everyone, welcome on board. And in our training Synamics S120 Parameterization Advanced, this is our first lesson and we will begin with basic positioner in commissioning. So I'm going to open our lecture notes and this is the index, and let's start with our first lesson. EPOS einfach Positionierung in German. In translation maybe it's not so correct. Let's say in English basic positioner and commissioning. You will see here our topics and index of this lecture. So our targets are, you will be able to configure the basic positioner and commissioning. Also, you will test your first functions and position controller inside the drive. You will be able to tune the current control loop, speed and position control loop, and you can test and customize your monitoring functions. Next page, here there is a basic block diagram of control side of the drive about the cascade controller. Our current control is the first step, is the first PID loop controller inside the drive. And before that is another controller, the speed controller generates our current set point and compares it with actual current of the feedback from the current transformators. And before that there is a position controller activated by us inside drive. It's generate the position set point, compares the actual position, feedback from encoder, motor encoder or external encoder, whatever. After that it will generate the position set point to the speed controller. And the first step, there is another additional EPOS object or function. It will generate also the position set point to the position controller. And step by step, it's a block diagram of our controllers. So there are some operating modes of basic positioner like jog and setup, homing, traversing block, absolute and relative positioning, and named as MDI, direct position input. And at the next page there is an example picture of application and use case scenario of our EPOS. In a factory there are some conveyor belts running like this. There is a rotary table with different kind of stations. There are some functions and there's a sensor for print mark correction or creating a new product running on belt for positioning or passive homing. There are two axes like X and Z for destacking and stacker system. Works together, two axes MDI positioning, for example. And the next page, for traversing profile, there's a path or target position set point or actual velocity. In our case there's no jerk, that's why acceleration and deceleration curve looks like this. For instance, there is a pulley or trigger belt up and down, and for positioning with different positions it's possible via drive. So basically there are two different kind of axes, rotary and linear axis. On the left side there's an example picture shows us the rotary axis. In normal case scenario it's endless traversing range, and motion commands can be a certain direction from clockwise or counterclockwise, or possible to travel over the shortest path. Usually we will use modulo like 360 degrees after one loop, and actual position of our motor encoder or the axis comes again to 0 by modulo. On the right picture example you will see linear axis. There's a positive and negative limit switches or software limitations. Also there's a defined traversing range at this case. And next page, for operating modes, for stacker unit we can use MDI. Via command we will switch between these states of our basic positioner function of the drive. For rotary indexing, for example, there are 6 different stations in our turntable, so that means 360 degrees divided by 6. In each step we will turn, for instance, 60 degrees, that means indexing. We can use MDI also here. Or for basic handling it's possible to program some traversing blocks. At this case, for the conveyor belt with print mark correction for new product, it's possible to use the flying positioning via passive homing. So next page, for integrating EPOS in basic functionality, there are some wizards to set up, control and monitor via online mode. This is a basic overview. EPOS functions like jogging or referencing or MDI or traversing, it will generate the position set point and the velocity set point connected to the position controller, and it will calculate the ramps or drive model or reference model and generates the speed pre-control. Also the position difference will be handled by the controller, and next step our speed controller. So there's a 3-level cascade control. And how do we do that? For activation in drive dataset, we will go in offline mode in configuration under our drive object, and in control unit CU320, or for single axis, for example CU310, we will select the basic positioner checkbox at the first page of the configuration wizard, and after that it's possible to select 3 different encoders for one drive object. Encoder 8 means motor side encoder, encoder 2 means additional mechanical external encoder connected via SMC30 module for example, to the drive click of control unit, and it will be possible to switch on the fly. And next page of our wizard, in mechanics tab, there are some parameters we have to define. At this case, we will select external encoder, and you will see here the red colored little rectangle box. For one motor revolution, we have to enter here length unit per load revolution, and you can consider this as micrometers. That means one motor revolution we will get in linear axis, for example 10 millimeters, and it is possible to activate here when you select the logic level 1. Then you can define here a modulo value in length unit. This is the related parameter number. And the next page, position controller and basic positioner traversing limitations. By default values for dynamic limitations, for instance, maximum velocity, maximum acceleration or jerk, we will define here, and it is possible to connect a parameter for activation of jerk limitation, maximum deceleration, and so on. So our comments, motion comments, afterwards will be limited according to these settings on the runtime. Okay. In our commissioning and service training, you have, if you examined and watched videos during the training, you have already used the control panel for commissioning the positioning functionality. After you go online and take up the control of drive, you will give enable. If this function is activated, you will see these buttons. You can test each function of basic positioning here. So it's a good thing for developers during on-the-field commissioning. And the next page, you will see how does a position controller work. It's a basic diagram to explain the main idea. So on the right side, from motor side or after the gearbox on mechanical side, we will get actual position from machine encoder or motor encoder. But you have to keep it in your mind. The speed controller of the drive works always with the motor encoder. Position controller of the drive can be worked in drive dataset 0, for instance, with motor encoder. In drive dataset 1 with machine encoder, it's possible to switch between two encoders during runtime. So there is an actual position source selection command. And here for three-phase power section, there is a current controller, speed controller, position controller, and EPOS is processing our logic. There are some inputs like reset or homing or offset correction for position controller. And next page, what are the core objectives of controller tuning? Dynamic response, stability, accuracy, ruggedness. And for tuning, we will use transfer function for step response. For each control loop we need to adjust the PID gains, integral time, reset time, and so on. And for a quick setting of P controller, there's a input set point and output actual value to tune the controller. And you will see here the advantages of cascaded closed loop control. It's possible to do step by step, first current and second step and third the position, and reduces delay times. On the left side you can work in time range or in graphics in domain like Bode diagrams. And here there is a simple block explanation. On the left side the basic positioner, on the right side the functionality of the drive. So, and before you do that, there are some preparation for tuning the position controller. And preparations, first of all you have to tune your current controller, and second step your speed controller, and the top of the control loop pyramid the position controller tuning. So first you have to disengage this one, velocity set point, and this one, position set point. So you have to disable the pre-control and disable the pre-control balancing. And for set point filter you need to enter here time constant to 0. And next page, and next stop, position controller, just enter here as P gain 1.0, reset time 0 millisecond, and PI controller settings adaptation here, and limitation you need to cancel. So after that you can use your trace functionality to get the signals and curves. And on the left side of the screen an example picture of the speed set point curve is too low. In the middle proportion gain is the optimum, and you see like this, it should be like this. On the right side when you enter it too much, it looks like the undershot or overshot. That means in your position set point, and you don't want this type of controller in application. It's not acceptable. So for tuned position controller, respond dynamically, and disturbance variance, it should looks like this: the speed set point accelerating and decelerating in tuned position controller, the actual position value as the red curve, yeah, and on the right side with different settings. So this is better. And effect of speed controller tuning, position set point jumps completely processed by speed pre-control. So you need to compensate the controller. And on the left side, when you compare on the right side, it's dynamically tuned by manual. On the right side with factory settings, it's non-tuned. There's some oscillation and vibration on speed set point and the actual position value, that means overshot or undershot. Normally with very short response time as a rise time, 1 or 2 milliseconds on the left side is better than the right side. The setting time is too much on the right picture. And at the end of this chapter, of course, there are some exercises for you to better understand the topics. So first, configuration of the basic positioner, EPOS. And second, set the home position. And the third one is optimization of current, speed, and position controller. So, at the first example for first commissioning, on the offline mode in drive dataset of drive object server 2, for instance, you need to hit this button, the yellow background, configure a DDS, and at the first page you need to select the basic positioner function, and you have to complete the wizard the following steps. There are some parameters you have to enter. And next page you will define the mechanics according to your real system or real hardware. So save your offline configuration. You need to go online and download your project into control unit, and you have to set up your hardware and connect the drive click cables and turn the motor and so on. So after you download in configuration, you will go online under the settings, homing in technology basic positioner. For setting the home position, the blocks should be looks like this. When you click here, a new window will open, and you can monitor the LEDs and the status bits. So if you connect some BICO parameter or digital input here, parameter R722.8, for example, for setting the reference point, then as result you will get the homed bit logic 1, that means reference point set. And the last exercise of this chapter, optimization. And as you know, in previous training and Synamics, you already know what to do step by step. You need to follow the stationary and turning measurement. After that, you have to automatic controller setting and speed controller set point jump in time domain and frequency domain as body diagrams, basically. And after that, you can optimize your position controller. You need to follow these steps already explained in this lecture notes. So far so good. And that's all for the first chapter, and see you later on.